So this should be a presentation about the basics of EPR for NMR spectroscopists. And from my subtitle, you could basically see that I think it's the same but different. So if you know NMR, I will not tell you anything fundamentally new, but I think there are a lot of twists and turns that kind of took a different way in EPR spectroscopy than in NMR. Like a quick disclaimer. So I wrote the abstract before I made the talk, and so I guess it was a little bit optimistic in things that we cover. So this is of course not a comprehensive introduction. So I just tried to show you some things that are hopefully interesting to you, and please ask questions if I was not deep enough and some examples. And also these examples are arbitrarily chosen, so it's not like I don't want to promote anybody, it's more about promoting EPR. And then also because of time restrictions, many of the explanations will be kind of hand waving. Yeah, you kind of have to excuse me for this. And I will also not say a lot about the chemical interpretation of spin Hamiltonian parameters. So we basically treat the spin Hamiltonian that we just want to know what the parameters are. And then there's still some work to do if you want to interpret this, but I will not talk too much about this. So like NMR, electron paramagnetic resonance or electron spin resonant deals with spins or magnetic moments in a magnetic field, and you excite them by pulses. So also the setup look quite similar. So if you compare an NMR magnet, we quite often use electromagnets in EPR, but some systems also use superconducting magnets. The difference comes mainly from the difference in gyromagnetic ratios. So the gyromagnetic ratio of the electron is about 660 times larger than the one of the protons. So the typical fields and frequencies are quite different. So we usually use field on 0.35 to 3.5 Tesla. Or these are then correspond to frequency above 9.5 gigahertz, 35 gigahertz, or 95 gigahertz. And these frequencies or these frequency bands have certain names, and it's called X, Q, and W band. And I think it comes from radar engineering, basically. And yeah, but there's nothing higher to this, basically. And this corresponds to rather low nuclear alarm frequencies, so proton frequencies of 15, 50, and 150 megahertz, basically. And we'll come a bit to the point why we use these low fields. Yeah, because it's very similar in physics, it's also very similar in mathematical description. So if you know about the block equations, the rotating frame, spin Hamiltonian approach, spin matrices, etc., you will have most, if not everything that you need to understand EPR spectroscopy. And this is kind of the aim of this talk, to show this to you. One thing that you of course know, if you do DNP, the higher frequencies comes from a higher splitting, and at the same temperature, this will also give you a larger Boltzmann polarization, which is of course the basis of DNP. But of course, many things that have nuclear spins don't have electron spins, so you cannot look at everything, but there's actually kind of a lot. So you can look at transition metals, either in catalysis, in inorganic systems, or in Mottella enzymes. You can introduce labels to proteins for structural biology. Some photoexcited states have a net spin. So for example, a triplet spin, where you have funny effects from the populations because they are not Boltzmann populations. Of course, if you have radicals directly in the reaction, you can study them by EPR. And something which came probably in the last 10 years, kind of a lot, are spin-based qubits. So a lot of many things that you see in quantum information processing were actually already done in NMR and or EPR. Of course, there are many different things that I haven't mentioned here. So I think the main part we should start is the interactions and basically compare it to what you know from NMR. And many, I highlight them here, you already know. So here we have the magnitude of the interaction and the frequency bands that we usually work at. And you see that the nuclear-Zeeman interaction you of course know as NMR. You know the nuclear quadrupole interaction if you studied it. Then when you have dipole-dipole interactions between electron spins, they have exactly the same form like in NMR. They are just larger. What you know is the electron-Zeeman interaction, but the treatment is slightly different in EPR than in NMR, and we come to that. Maybe you've heard, or maybe you've not heard about the zero-field splitting of high-spin electron systems. And then basically what I have to highlight at the start is that in EPR, usually we cannot distinguish chemical shift J couplings or nuclear dipole-dipole couplings because they are usually under the line width that you can achieve. So homogeneous EPR line width would just be, is usually broader than ENDOR line width. And we'll come to this, how we can increase the resolution basically from our spectra. And just a quick thing to this. So if you're dealing with sequences where it's about hyperfine interaction, we usually call them hyperfine spectroscopy, but it's just a subset of EPR techniques. And if you talk about dipole-dipole coupling between electron spins, we call them pulse dipolar spectroscopy. But there's nothing really more to this. It's just different pulse sequences, basically. So let's dive right in. So we start with the g-Anisotropy, and there was actually a very nice introduction, I think 2 weeks ago by Björn Kortzelius, where this comes from, and with a little bit more detail that I will give. So usually this is an interaction between the external field and the electron spin. And you have an interaction G matrix, which we call G matrix or G tensor. And for the free electron, I mean, this is isotropic and this is known to very, very, very high precision. But in bound systems, you usually have deviations from this value. And it's due to spin orbit coupling of excited states. And I put this into quotes because there's, of course, a lot of theory going into the statement. But let's just say in different systems, this G tensor can be different. And in a way, in terms of information content, it's similar to the chemical shift. But we see that it's quite different in magnitude. And so for this, I made some simulations at 1 Tesla. And so at first, let's say we have just 1 ppm broad line somewhere around 28 gigahertz. And so I made the scale in gigahertz here. So this is a simulation of a tritial radical that I use at my lab. And I just looked at this, and it's would be roughly 500 ppm broad. And this is what we call a narrow line in EPR. It's actually a pretty narrow line. If you're looking at nitroxide radicals, which are quite often used, this would be the width in the frequency domain. I mean, we usually don't measure it like this, but it's just here for illustration. If you go to a copper 2 system, a typical one, this is how it would look like. So here you're more in the percent range than in ppm. And if you go to a high spin cobalt 2 complex, it's actually a little bit more complicated. It's not really g-anisotropy here, but it doesn't matter at this point. Yeah, you see that this is extremely broad, and it's kind of silly to plot it like this because, of course, nobody measures it like this. But it was just here for illustration. And the width of these spectra scales with the magnetic field because it just comes from the anisotropy of the G tensor. So depending on what you want, it might not help going to higher field because, of course, the G resolution gets better at higher fields, but of course, you also get broader spectra, which doesn't necessarily help spectroscopically. And of course, also, even if you have the fastest magic angle spinning, probably in 10 to 20 years even, you will probably not be in the tens of gigahertz range. So for most experiments, MIS would probably not help. There are some MIS EPR experiments, but it's usually not done. Then the next important interaction is the hyperfine coupling. That's the coupling between the electron and the nuclear spin, and which is also a tensorial interaction. It has 2 main contributions. So one is from the dipole-dipole coupling, which is anisotropic and traceless. It's proportional to the gyromagnetic ratios and to the distance between the electron and the nucleus. But of course, you have to keep in mind that the electron is usually delocalized. And so a point dipole approximation is not necessarily good if they are close together. They can actually also be at the same position. So you also have a Fermi contact contribution, which is then isotropic and is proportional to the spin density at the nucleus. And because we will need it later, a very common situation is that the hyperfine coupling and the nuclear Zeeman interaction here are on the same order of magnitude, but at the same time much smaller than the electron-Zeeman interaction. So we can then use the high field approximation, but only for the electron. So we truncate the Hamiltonian to all the terms who only have SZ, but they have IZ, IX, IY, and then we usually also turn the nuclear coordinate system that we just have this A term and B term. So ASZ, IZ plus BSZ, IX, which are called secular and pseudo-secular terms. You see that the isotropic component also only contributes to the A term, and the rest is basically, if it looks like a dipolar coupling or just a second rank contribution. And for the point dipole approximation, we have a nice expression for this T, which would then give you information about the distance between electron and the nucleus. Now the dipole-dipole coupling between electron and the exchange coupling, they are mathematically, and they have the same form like in NMR. They are just much larger. So here, because the dipole coupling scales with the gyromagnetic ratios, and you have this one 2 times. So if you have this peak pattern, then the splitting of these peak patterns will be 52 megahertz at 1 nanometer. And I think for protons, it would be 120 kilohertz at 1 angstrom. So it's much, much larger for electrons. And keep in mind, if you have very large g-anisotropy, basically the quantization axis of your spins might not be the same for the two. So this gets more complicated. But we will not treat this contribution here. The exchange coupling also has the same form like in NMR. And basically what this gives you is it comes from an orbital overlap of 2 electrons. Now, because these interactions are so strong, it's actually not always better to use high concentrations. Because at some point you get strong electron-electron interactions. And if you want to know about basically a molecular system where you're only interested in one electron and the surrounding, usually we use concentrations of millimolar or less. So 10 millimolar would already be kind of a lot. Depends on the exact spectral properties, but in general, this is the order of magnitude. For dipolar spectroscopy, it's even less. Then what we're missing is the zero field splitting, because there is only there for if you have an effective electron spin of higher than 1/2. So you need strongly coupled electron basically to see this. Then you get an effective spin. And you see here, it's like S times D times S. So it already looks kind of like the quadrupolar coupling. And then I think this is kind of an unfortunate parametrization, but you have this D and E value for the axial and rhombic components. But so in general, it's quite similar to the quadrupole coupling in NMR. It's traceless, has an axial and rhombic component. If you have half integer systems, which you also call Kramer systems, you get a central transition. And then something which is probably not so familiar from NMR, if your zero field splitting is much larger than the microwave frequency and you have integer spin, then your system is basically EPR silent because there's just no, there's no transition in reach basically for you. Of course, if you go to higher frequencies, this might change. For half integer system, if the zero field splitting is much larger than the microwave quantum, you can get like things like effective G values. So basically at zero field, then you still have degenerate levels and they split up and you can actually induce transitions between the two. And then it looks like a G tensor, but the only information you have in there is basically you get then something about E over D. So basically you get information about the rhombicity of the tensor, but you don't get the absolute values of the zero field splitting. but I think it's just good to know that this can happen. Now, basically, I think the first question most NMR spectroscopists have, if they have not heard a lot about EPR, is why we still use CW. The reason is that our spectral width is usually much larger than the gamma B1 that you can achieve. So if you look at the excitation profile of this pulse, if you do an FID and a Fourier transform, what you would see is the excitation profile of this pulse, and not really the spectrum here. Then usually we use microwave resonators, and then the frequency sweeps would also be very cumbersome. So going through this step by step would be very cumbersome, or sometimes even impossible. So you would need broadband sources that can do this. So what we usually do is we have a fixed microwave frequency, a high Q resonator, and we sweep the B0. And what we usually do on top of this is that at every field point, when we detect, we modulate the field a little bit. And this gives you basically a better SNR, and it gives you the derivative. So let me explain this shortly. So if this would be, the black line would be the absorption, basically, the EPR absorption. And now imagine we're at some point in the B field here. And now instead of staying there, we modulate this a little bit with a frequency that we know. Usually it's about 100 kilohertz. Then the absorption will oscillate between this point here and this point here, right? Depending on where you are exactly with the field. So this gives you basically an intensity modulation of your signal. And if you now plot the amplitude of this modulation as a function of the external magnetic field, what you get is actually a derivative line shape. And of course, you cannot, if you modulate much broader than your peaks are, this will not work very well. So usually you have to kind of know how you do this exactly. But this is why we have this strange line shapes, basically. So let me give you a few examples. So this would be a radical in solution. You have one unpaired electron, which would be delocalized. Then you would have a group of 3 equivalent protons in one, a group of 6 equivalent protons labeled by 2, which would give you a septet of a quartet. And if you look at the spectrum, solution spectrum of this, this is what it looks like. And usually, if you see this the first time, it's kind of strange because you see kind of double peaks because it's derivatives. But let me just highlight. So this would be the quartet here, these 4 lines, and then this would be repeated 7 times. Yeah, and you also see that I put the simulation and an experiment here because it's actually the usual case that you have to simulate your spectra and fit to even get to the parameters that you have in your spectrum. Here it's of course easy, but for the following examples, it will be much harder. If you want to do this simulation, there's actually an Easy Spin Academy going on right now, so at the same time, just go to this website. It's a very nice MATLAB-based program. So let's go a little further. So this would be more complicated if you have one of these copper complexes with axial symmetry, S equals 1/2. You have an axial g-anisotropy, but you also have an anisotropic hyperfine coupling to the copper. So basically for each sublevel, so for each state of the nucleus, you have a different EPR spectrum, and it's basically given by the g-anisotropy that you have here. And so this would be parallel to the magnetic field. This would be perpendicular to the magnetic field. And now you have a splitting depending on your nuclear spin state, and it's also orientation dependent. So here you have a large splitting if it's parallel. So you have a large AZ or A parallel, and here basically a vanishing coupling in the plane. If you look at the derivative of this, it gives you this spectrum. So here it actually still looks like absorption, but it's because it's this derivative of these stairs. And the splitting here would be your hyperfine splitting in this orientation. And you can imagine that this gets complicated pretty quickly. And this is basically why we simulate. So these easy examples you can basically understand by experience, but at some point you usually need spectral simulations. So just another important example is this nitroxide. So spin 1/2, coupling to the nitrogen, and G as well as A are anisotropic. So at X band, it's actually the hyperfine coupling that dominates the width, but already here it's not obvious to see how the spectrum actually arises, and I don't expect you to. I want to show you the example. At Q band, you kind of see the g-anisotropy coming in. I just plot the derivative at the bottom, but I think you're more accustomed probably to the absorption line shape. And then at W band, you see actually that the g-anisotropy is actually the dominating factor for the width. So here at this point, you have the ZZ, and the ZZ is split by the hyperfine coupling in the Z direction. Here will be Y, and here will be X. And then just one more thing that I would like to tell about CW, because this is quite useful, especially for nitroxide spectra. So this here on top would be an isotropic nitroxide spectrum in solution. So 3 lines and isotropic hyperfine coupling. And then basically, if you have increased the rotational correlation time of the molecule, it gets broader and broader and gets this kind of different shapes. And at some point, you will, of course, be in the rigid limit. But this is actually very useful if you're studying, for example, a spin label attached to a protein, because you basically immediately see whether you bind to a protein, because the line shape of the nitroxide changes very differently. And there are some funny effects that you see, for example, here, that the first line here becomes smaller first. And this is some correlated G and A relaxation, basically, that you find there. It's a very complicated theory to go through. So I think at this point, we will take a few questions.
Okay, thank you. That's really interesting so far. So yeah, please type your questions into the Q&A box. We have one question already from Kevin von Witter, who's asking, what does high Q mean when you're referring to EPR resonators? I
think it's a few thousand, if I'm correct. I guess it depends a little bit on what Q you have, but so yeah, I'm not doing a lot of CW, but that's what I have in my head. So it's very narrow. But I mean, you cannot do any Pulse EPR with a CW resonator. Basically, you have to do the coupling very differently.
And could you explain why you need such a high Q factor resonator for EPR, for CW?
So basically, you just get a lot more signal because it kind of amplifies it when you. So you can use a very low microwave power then. And then also the detection is basically proportional to your Q factor, the detection sensitivity. So that's why you want to use a high Q. I think the phone is, that's the phone. Oh, no,
it's not very loud. It's okay.
Oh, okay.
All right, thanks. Okay, a question from James Ives. Is there future scope for moving away from CW EPR with engineering improvements that would allow for broader pulses?
So I guess that's, I'm using this like broadband pulses, so I guess yes. But in a way, I don't think I'm not sure if we will abandon CW totally, because you have seen how broad they are. I mean, they are totally in the % range at some point. And let's say the electronics are very far away from being general. I mean, there are some systems where nitroxides at Q band or W band, you can now excite with one pulse. That works. But for these very broad systems, I don't know. And there's one technique coming up, which is called rapid scan EPR, where you do it more quickly and basically use fast passage. And then you kind of reconstruct the signal. But it's also, I think Brooker does it now commercially, but it's not, yeah, the CW still dominates at the moment. Let's put it like this. And I don't see it completely abandoned within the next, let's say, at least 5 years, maybe.
Okay. So I don't see any further questions for now. Please do keep asking questions. We'll have more opportunity to go through them later. And please continue with your tutorial.
Okay. Well, that brings me basically to the next step. So Pulse EPR, which I think will also be the nice thing for NMR spectroscopists, because that's what you know. Again, we usually cannot cover the whole spectral width. So we cannot really do one pulse in Fourier transform. So we usually don't have a direct dimension, but what we do is we integrate the echo intensity, and you'll see why we use an echo, and then do something basically in between. We manipulate the spins that lead to a different echo intensity. So what we use it for is basically separation of interactions, because we can still decide like which one do we want to keep, which one do we want to see. And one other problem is that we have fast relaxation, and the typical here is really in quotes because it's all over the place basically. But if you have a copper 2 system, then you usually have we call it phase memory time. It's kind of a T2, but just for the echo. It's usually a few microseconds, and T1 is in the order of a millisecond, but at 10 Kelvin, right? So at room temperature, most of these things relax so fast that you can hardly do Pulse EPR. So for some radicals, or if you have a very special arrangement around your metal complex, this might also work at room temperature. But in general, the majority of Pulse EPR experiments is done at low temperatures. And we use pulses in the nanosecond range. So typical pulse lengths are like 1632 nanoseconds. And the problem is that we have a dead time of about 80 nanoseconds. Depends on the resonator exactly that you have and your spectrometer. But if you look here, if this is the nitroxide spectrum, if you could excite this the whole time, and if you have a dead time of 60 nanoseconds, which is pretty optimistic, well, you're not going to see anything with an FID, basically. So we basically, all the sequences that you're going to see will have an echo detection. One thing that you're probably not familiar with in NMR is orientation selection in pulsed experiments. So this would be an anisotropic spectrum. And here I take axial symmetry just for the sake of illustration. Now, basically we can choose, we have a fixed frequency of our resonator. And now we can choose the magnetic field where we do our experiment or our pulse sequence. And we have to decide because we cannot excite the whole spectrum. If we decide to do it here, you only excite these spins here, and these actually correspond to a certain orientation that I highlighted on the sphere here. So basically, if you do it here, you're very selective for molecules that are aligned with the external magnetic field. If you choose another field, you choose another angle basically of this distribution. If you do it on the maximum, basically you're choosing spins that are in the XY plane. And so, I mean, this is there. It can be good or bad, depending on what you want. It's nice to get relative orientations of tensors. You have hyperfine and G tensors, but it's not so nice if you would just have the whole information in at one field, basically. So, but it's usually present. And of course, quite often it's not that easy. So if you look at the X-band nitroxide spectrum and you decide to sit on the maximum of this, you just excite some fraction of orientations of your molecules. And usually you hope that orientation selection is not that significant, or usually you have to simulate it somehow. So only in very easy cases can you really follow by hand what exactly the orientations are that you excite and how this translates to the spectra that you will get in the end. So the first topic that we will cover is hyperfine spectroscopy, so detecting the interaction basically between nuclei that are close to the electron spin. But we do it with EPR. So basically for everything I show you, we'll always detect the electron spin in the end. But we learn something about the nuclei that are close to it. And then you can get nuclear Zeeman interaction, get the hyperfine interaction, and the nuclear quadrupole. Especially the nuclear Zeeman and the nuclear quadrupole, they don't show up to first order in a normal EPR spectrum because you don't excite any transitions that change these, basically. Then keep in mind that the hyperfine coupling can be larger than the nuclear Zeeman frequency, which leads to funny effects. The resolution can be much, much improved. So even if your spectrum is gigahertz broad, your normal CW spectrum, you might resolve couplings that are less than a megahertz or 0.1 megahertz or something. or even less if you're, but then usually you have to have a special system or be lucky a bit. The problem is a bit that it's an absolute zoo of techniques. So I think even if you do EPR, you think it's a zoo. There's no one-fits-all solution because it always depends on what the system you have. What are the relative magnitudes of interactions? How fast does it relax? How much do you have? Like, what's the concentration? So unfortunately, it's a little bit complicated there. But I'll give you an overview here. So the one which I think is conceptually the easiest to understand is ENDOR. So it's electron-nuclear double resonance. And what you do there is you use microwave pulses and RF pulses at the same time. But you always detect the electrons. But we will see how it works in more detail afterwards. Then there's so-called ESEEM, which is electron spin echo envelope modulation. And there you only use microwave pulses. But because you have semi-allowed forbidden transitions, basically you get nuclear oscillations on your echo decays, which give you information about the nuclei that are present. And there's actually a 2D variant of this, which is very, very useful, which is called HYSCORE, or Hyperfine Sublevel Correlation. And the last one, which is not used that much, but I think I included it anyway, it's electron-electron double resonance detected NMR. There you have two microwave frequencies and basically use a polarization transfer via forbidden transition. And in a way, it's the same as the solid effect, but instead of detecting the nuclei in the end, you detect an electron with a certain offset. But you basically already know how this works. That's why I put it in here. Then, I mean, at the end, there will be the choice, which of these do you choose? And I think it's just a little bit too much to put into this talk. So depending on how strong your interactions are, you might choose different ones. But quite often, it also just boils down on what you can do, right? Because not everybody has every spectrometer equipped with everything at every field that you could possibly wish for. So let's start with ENDOR. And this is just a certain type of ENDOR. There are other ENDORs. Everything where you use microwaves and RF pulses basically we call ENDOR. And here first, basically you use selective pi pulse on the microwaves. So basically you burn, if you have a broad EPR spectrum, you select a certain frequency and you burn a hole there. It's not really long and weak in this case, it's more a pi pulse, but it's just an inhomogeneous line then. Sorry, here you have the homogeneous line width or the excitation pattern of your pulse. What this does to your population, if this is the electron-nuclear level diagram, usually have polarization only on the EPR, or it's much higher on the EPR transition. So we just neglect the NMR polarization. Now, if you have a selective pulse, you invert one of them. And it could be any of the two, but let's choose one. And now you see that actually you have polarized NMR transitions. So at this point, you can actually use an RF pulse. And what you do with this RF pulse, that you step it in frequency. And depending on which transition that you hit, you have a different effect. So if you hit this transition here, you see that in the end, your electron transitions are actually saturated. And so the echo that you detect in the end will be smaller, just because you used this NMR pulse basically in between. If you don't hit anything, then your detection here, which is at the same time where you burned the hole, usually will be unaffected, or it's inverted as usual. And also if you hit the other transition, you will have an effect on the electron spin intensity. So I think this is quite good to follow. It's really just shuffling polarizations basically. And you have to generate this non-equilibrium state here that the RF pulses actually do anything. And so this microwave pulse has to be selective. So you cannot use a broadband pulse. It has to be smaller than your hyperfine coupling basically. This is the point. And with this, you can get some very nice spectra. So this is an example of manganese GDP inside a protein, and you can measure the coupling between the electron spins on the manganese atom to the phosphorus. So here a W band the phosphorus frequency would be around 57 megahertz. But then you see a splitting if your RF frequency hits these transitions. You see the splitting, which has an isotropic component. So they are always basically apart. And then you have some anisotropic dipole component on top of this. And actually, this doesn't really work for very small couplings because you need this selective pulse, and you can only do basically, if you still want to have a signal, you can only choose the excitation bandwidth so narrow. At one point, you just don't have a signal. But there are other ways to do this. So there's a MIMS variant of ENDOR, which I'm not going into, but then you can also resolve these smaller hyperfine couplings to more remote phosphorus atoms, basically. And now I want to come, I think actually one of the main differences between NMR and EPR, at least if you're not talking about low field NMR, because in these low field conditions and EPR, and because we have this large hyperfine coupling, you get forbidden transitions. And I want to spend some time with this. If you do solid effect DNP, you kind of know it already. If you look at this Hamiltonian, it's actually block diagonal. Because we only have SZ terms, but we have an IX operator as well, not only Z. But for a different MS manifold of the electron spin, they're not diagonal in there, but they are diagonal with respect to the electron spin. Let's put it like this. So you can actually rewrite this in terms of S alpha and S beta operators. So S alpha just has a 1 here, S beta just has a 1 here. And you can look at this geometrically because you have IZ, IZ, IX here, and you have IZ, IZ, IX here. But the coefficients are different depending on the spin state of the electron. So what this leads to, if you add these together in a vector diagram, basically, you see that the frequencies of your nucleus, this omega alpha and omega beta, depends on the electron spin state. And it's not only the magnitude that depends on the electron spin state, but it's actually also the direction, because you have this pseudo-secular term here, this BSZ-IX. This leads to some funny effects, because of course, if you're in this state here and you flip the electron spin, suddenly your quantization axis is not aligned anymore with your nuclear spin. And then basically, that's how you generate these forbidden transitions, or it's one way to look at this. So you can use a propagator to diagonalize this, which can just use basically normally as in product operator formalism. So you can use your Hamiltonian and you can diagonalize it, and then you get terms basically with your nuclear frequencies depending on the electron state in this Hamiltonian. And here it's diagonal. So this is diagonal. But then you also have to put your excitation operators into the same frame. And if you use SX, you transform it to the eigenbase or the diagonal basis of your Hamiltonian. You see that with a certain probability, you actually excite electron-nuclear transitions. And this eta is basically the angle between these two states here. So the angle between the quantization axis of the nuclear spins in the different electron manifolds. So basically, the larger the B is, the larger this forbidden transitions excitation will be. And also you see it here if basically you have an exact cancellation. So if A half and omega I, sorry, are exactly the same, then you have the maximum of this transfer. And this is a situation that you can encounter in normal EPR experiments. So this would be the energy level diagram. Again, you have EPR and NMR transitions, but you also have these forbidden EPR transitions. And if you center on the offset of the electron spin, you get basically 4 lines. So you kind of get the allowed transitions, which are split by the hyperfine coupling. But then you also get these forbidden transitions, and the difference between is roughly 2 times the nuclear Zeeman frequency. And of course, in solid effect DNP, you look at systems where the hyperfine coupling is much larger than your omega I, and then you have forbidden transition at the electron spin offset plus minus omega I. So this is basically the green ones are kind of more or less at the same point. So you can use this in different ways, and the first one is easy to understand, I think. So this ELDOR-detected NMR, we use 2 microwave frequencies, and it just uses this solid effect. So we burn a hole, and then we detect the electrons at a different frequency. And if you have this level diagram, and you hit, let's say you hit one of these forbidden transitions, then what you do is you pump population up here, going from here to here. So you produce nuclear polarization, which is what you need in DNP, but actually also saturate the electron transitions. I mean, of course, in reality, it's never saturation. It's just as an illustration here. And in a spectral way, if you hit one of these forbidden transition, you actually produce holes at an offset of where we irradiate it. And the offset to these side holes are actually the nuclear frequencies. So usually what you do is that you observe at the fixed frequency, and then you change the frequency of your hole burning pulse. That's what you usually do. And the spectra then looks something like this. So the original one is the one with the red line here. So of course, you saturate your signal if the hole burning pulse is exactly on resonance with the observer pulse. Then that's why you produce this kind of hole here in the center. But then if you go to higher offsets, if you change the frequency difference between hole burning and observation, you actually start seeing these side holes, which encode the nuclear frequencies. So here you see phosphorus. This is the combination line. You see sodium, nitrogen, and here for the protons, which is not really resolved because the hyperfine coupling is very small. But in the case of phosphorus, the coupling is large enough that you actually see 2 different lines. And of course, if you irradiate, this is basically what gives you DNP, but you just detect it on the wrong side, basically. Yeah, and also the width of the central hole is given by the power that you use for the hole burning and by relaxation. And so you can imagine if you do this at very low fields, all these frequencies will be nearly the same, and they will all be obscured by the central hole. So this ELDOR-detected NMR is usually used at fields from W band, so 150 megahertz proton frequency. Yeah. Okay. Then maybe we do questions now, because I think the next part will be a bit more bit heavier. So let me see quickly. We have here.
Okay, great. Yeah, so we already have a few questions. Sticking with the ELDOR, because we're here, Adam G asks, is the observation pulse in ELDOR always fixed? And do you set it to the center of the ESR line or somewhere else? Or?
So you usually let it fixed because, again, because the detection is just most sensitive if you do it in the center of your resonator. So because you have some resonator and then you have to step, one of the pulses basically has to change somehow. So you usually leave the observation fixed. And but you can do it at different points of your spectrum, and this is where this orientation selection might actually come into play. So depending on where you do it, you might get different couplings, because for different orientations the couplings might be different. Does that make sense? I mean, I guess usually you start at the maximum to get something, but then yeah.
Great, thank you. So sticking with ELDOR, I actually had a question. Why does your 55 manganese come at a higher frequency than phosphorus? So that's not how I learned NMR.
Because manganese, because the hyperfine coupling to the manganese here is roughly 250 megahertz, I think. So actually it's in a strong coupling regime. So the coupling is much larger than the Zeeman frequency. So actually there's another line somewhere out here, and the center is half the hyperfine coupling or something like this. And then the splitting is actually the Zeeman interaction.
Okay, interesting. Thank you. So you mentioned the orientation selection again. So an anonymous attendee asks, are there any applications where you combine orientation selection media, so alignment media used for residual dipolar couplings in NMR to align your EPR and use that orientation selection?
I think there is. I think Jack Fried looked at, but then mostly dipolar couplings, if it's in bicells or not. But generally, the problem is, of course, that RDCs assume that you're in solution, kind of, or right, that you have some alignment media, and usually we do it at 10 to 15K. So yeah, it's just frozen. Nothing actually moves anymore. So yeah, I don't think it's used that much, or I don't know that many applications where it's system.
Okay, thank you. Another anonymous attendee asks if you can explain the difference, or a simple explanation of the difference between MIMS and Davies ENDOR.
Well, I mean, you have to generate this non-equilibrium populations, right? Somehow. So somehow you have to generate a situation where we can actually use RF pulses. Otherwise, nothing will happen. Davies ENDOR does it with a selective pulse, but basically you can also do it by pi half tau pi. So basically you have antiphase coherence, which then corresponds to, which depends on the hyperfine coupling, and basically you can generate the situation also with pulses and delays. But then you can get some blind spot and stuff. But yeah, that's the.
Okay, thanks. And then a final comment from Thomas Schmidt referring to the CW EPR in the first half. A comment that you can get distances from CW EPR even if they're small.
Yeah.
So
I'm coming to that.
Comment on that. Okay, great.
Yeah.
Well, on that note, then keep going then. Thanks.
Okay, then I think now we talked about forbidden transitions. That's okay. And we talked about ELDOR using polarization transfer via the forbidden transition. And now the more complicated subject is they also have effect on coherence transfer. And because we're already in 47 minutes, I would like to shorten this quite a lot and just describe the problem and not what you get out too much, or how it's exactly done. If you look at this sequence here, pi half tau, pi tau, and then echo. If you think that the B term is away, it's very easy to describe because everything just refocuses if you just do it on the electron spin. But the point is that if you have this coupling, it doesn't. Because you cannot just use the product operator formalism because this term doesn't commute with the rest, right? I mean, you can do it numerically, but not analytically like this. So, but what you can do, you can transform the Hamiltonian into its eigenbasis. And there everything commutes. So there you could compute the what happens in the free evolution times. But at the same time, you have to transform your excitation operator into the same frame. And then you have here two different terms which do not commute. So what you have to do is for every pulse, you have to be in the normal rotating frame, and then you have to transform to the eigenframe of the Hamiltonian to describe the free evolution here. So instead of having to compute pi half x tau pi x tau echo, every time you go from a pulse to a free evolution, you have to use this diagonalization operator here, which gets very cumbersome very quickly. So it's actually quite a pain to do it even for this sequence. And we will, of course, won't do it. I just show you the result is that if you look at this echo decay, you not only have a decay, but you have small oscillations on top of this decay. And if you go through this whole thing here, what you end up is a modulation formula that looks like this, which is already quite horrible, even for a two-spin system and just a two-pulse echo. So you see modulations with the nuclear frequencies, and you have some modulation depth. And basically, this modulation depth scales with how strong the forbidden transitions are. But not only do you get these normal nuclear lines, you also get difference and some frequencies. So you have even more frequencies than we'd expect, and they are actually quite broad. So they are limited by the relaxation time, basically, of the electron spin. So we can do better. And this now you will just have to believe me, but if you go through the same formalism, a sequence pi, pi half, tau pi, if you have this forbidden transition, actually generates nuclear coherence. So at this point, you actually have nuclear coherence with some probability. So it's sine eta, cosine eta. And then you can actually let this evolve for some time, and then you can transfer it back to observable electron coherence. So this is what we call 3-pulse ESEEM, because it's 3 pulses and it leads to an oscillation. And here, the thing is that you have much narrower lines than in 2-pulse ESEEM, and you don't have the sum and different frequencies. I'm not going to show you the modulation formula because it's even more horrible than for the 2-pulse case, if you write it down fully. So on top here would be the 2-pulse ESEEM, and at the bottom here we have 3-pulse ESEEM, where we see, in this case, you have protons and you have a nitrogen there. So you see the nitrogen frequencies including the quadrupole, and you also have double quantum frequencies here. But I won't go through the math. Basically, you saw the problem, you know how to do it. So if you're interested, you can either do it yourself. I think there's something in this paper here that does it a little bit more detail. The problem here is that it only, basically the generation of this nuclear coherence depends on the hyperfine coupling that you have and on the tau that you have. So actually, if you do this for different taus, you see that you have tau-dependent blind spots. So if you want to observe this line here, at some point, depending on the tau you choose, you actually don't see anything. Yeah. And then we come to this hyperfine sublevel correlation. And this is the same as the 3-pulse EC. So you have evolution of nuclear coherence. But now we have 2 evolution times, T1, and this should be a T2, not a 2, sorry. And we have a pi pulse in between. And what this pi pulse does, to first order at least, is that it flips the electron spin from alpha to beta or beta to alpha. So you exchange nuclear frequencies. So you go from alpha to beta or to beta from alpha. And this, of course, helps you with this. If you have several peaks, it helps you strongly with assignment. So you get this 2D peak. And if your hyperfine coupling is much smaller than the Zeeman frequency of your nucleus, you're in this positive quadrant. And so you're centered around the nuclear Zeeman frequency, and the splitting is given by the coupling. It's also possible that the coupling is larger, and then actually it's in another quadrant, and it's split by 2 times the nuclear Zeeman frequency, and it's centered around half the hyperfine coupling. I kind of skipped over this in the introduction, but this is basically also what Michael asked about the manganese, that you kind of have this rigid coupling regime. And here it's, of course, much easier to know which doublets belong to each other. And so I guess here we have a nice application. So this is an iron-iron hydrogenase. And here the question was basically how this was assembled. And then they used kind of labeled serine. And you see, if you compare the unlabeled one with the labeled one, you see popping up at the nuclear alarm frequencies of carbon-13 with a certain splitting. You see peaks coming up here. And at the nuclear alarm frequency of N15, you see these peaks coming up here, which basically says, okay, that this 15N has to come from this serine. Yeah, and there it's much easier to do this assignment in 2D than in 1D. Okay. Then I think, yeah, I mean, I glossed over this rather quickly. It's, if you really go through the math, it's let's say cumbersome, not overly complicated, but cumbersome. Yeah. So maybe I think I see one more question. So I just take it.
Okay. Yeah. So Quentin asks, in the 3-pulse ESEEM, is electron relaxation during your T delay an issue, or are you only concerned with the nuclear coherence during this delay?
Okay. So it's not really the relaxation that is a problem of course, if you have very fast T1, if you relax everything back, then it is a problem. But what is usually a problem in terms of resolution is that you have spectral diffusion between electron spins. So because here after this, not all your electron spins are in the same state. And then if you have other electrons present or something else happens in between here, I mean, also some exchange or whatever, this will also be an issue. But basically, if T1 relaxation is already an issue, it's too fast, then you usually don't even see an echo. So that's why I think.
So what sort of ballpark numbers would you use for the T delay?
Well, it's still in the microseconds range usually, but your lines are so broad anyway, usually, you know, that you don't have to do it forever.
Okay.
Yeah.
Okay. Okay, yes. So another anonymous attendee asks, are the Hyperfine experiments tolerant towards the pulse flip angle? How well do you have to set that?
Well, I mean, in general, if you put a pulse into the center of your spectrum and you excite only a very small fraction of it, then the flip angles will be bad for most of the spin packets that you have. But it's not so much an issue here because you just do phase cycling, basically. This, I mean, of course, the transfer might actually be sensitive to this. So especially in this high score, when you need this pi pulse, this has to be a good pi pulse that this works well. But you just, I mean, you get basically for all the 2 pulses that you have, you get an echo. So if you do this in a machine, you actually see an echo here, and you also see like other echoes here. So you have to do phase cycling anyway to get rid of these. I guess this is, yeah, this is how you usually do it.
Okay, thank you. So a question from Dima. Can you comment on the use of AWG in EPR experiments? And for my benefit, can you also say what AWG is?
So it's an arbitrary waveform generator. So I think I think this is already normal in NMR, that you basically just digitally program your pulses, and you can do like swept pulses or anything. And basically our group, among other groups, we're working at using these for EPR experiments. It's not very widespread, but some obvious applications that you know from NMR are broadband inversion pulses, where you can use chirp pulses to invert, or Gaussian pulses to be more selective or have a nice selectivity, things like this. So I would say it's coming up, but it's not normal yet. Let's put it like this. I mean, there are AWGs in the modern Brooklyn machines, but I haven't seen them used that much yet.
Okay, so watch this space. A question from Thomas Schmidt. Is there a difference in distance, proton-electron distance dependence, or proton population for the 2-pulse and 3-pulse ESEEMs?
I guess you mean distances that you can detect, I assume?
Yeah.
I mean, the modulation formulas are a bit different, but it's mostly determined by the intensity of these forbidden transitions. And of course, the resolution is much worse in 2-pulse ESEEM. So basically, if you want to see a small hyperfine coupling, which corresponds to a larger distance, then it's better to use 3-pulse ESEEM. But I'm not entirely sure if I got the question correctly.
Okay, well, Thomas, do either raise your hand or ask another question if we've not answered that one fully. In the meantime, a question from Jeffrey Bodenhausen, asking if you can elaborate on coherence transfer pathway selection by phase cycling. Okay.
Yes, in the sense that it turns out that you cannot really determine the phase of this nuclear coherence by changing the phases of your electron pulses. So basically, you cannot really, you know what I mean? So usually you could choose the phase of your nuclear coherence with the pulses on this nucleus. And here you cannot really do this. So basically, everything that you have in terms of coherence pathways are just of the electron spin. And it's usually, if it's a 1-spin system, it's just -1, 0, or 1. And the problem usually boils down to selecting the echo that you want. But of course, you have to design the phase cycling with the usual coherence transfer pathway scheme, and then you can figure out what is the best way to get only the echo that you want. Because otherwise you might have, so if you look at an echo which comes, I don't know, from this pulse and this pulse, at some point, these might actually go over the echo that you want. So then you have strange spikes in your traces, but you usually immediately see it if this is very bad. Yeah, but this is what you usually need phase cycling for in EPR.
Okay, great. Okay, well, it doesn't look like there are any more. Okay, I do have another question from anonymous attendee. What is a typical T1 row in EPR? And can you use spin locking for magnetization transfer in EPR?
I like the question because my last paper is basically on a spin locking technique, but it's not very usual to do this because the thing is that, again, you usually cannot lock the whole spectrum, right? You just lock a very small part, and then it's usually not really a T1 row that you measure. It's just some decaying magnetization that comes from very different pathways, but it's from the very little experience that I have from my experiments, it's usually longer. And if you can do a proper T1 row, it's much longer, but I cannot measure it as long as it is because our amplifiers can only give a certain length of pulses. So, but it's not, there are not really experiments that really make use of this at the moment. Might change in the future. Yeah.
Okay. Well, I guess check out Nino's paper for more details there. I'm going to ask if there are any more questions again, because then one will appear. No. Okay. If not, please join me. Sorry, say again.
I mean, I could show a little bit more, but I'm not sure if we should just stop. I could just say a little bit about bipolar spectroscopy.
Okay. Yeah. Please go ahead.
I guess
we've still got 65 interested people, so.
Okay, I mean, if you drop out, basically, I know that I stopped, and I keep it very short. So what this is usually used for is that you put labels into proteins, and then you can see kind of large domain movements. And the nice thing is that you cannot only get distances, but you get these distance distributions. This is very nice for systems where you might know something about the structure, but you don't know all the details, and maybe you cannot crystallize it, etc., etc. I mean, you know it basically from solid state NMR, and it gives you these long range interactions basically. So usually you put these labels in, you have a dipolar coupling between them that you all know. And here is something that Thomas wanted me to show. In a typical X-band nitroxide spectrum, this would be the corresponding Pake pattern. So if you have a very small distance, it might actually be possible to kind of resolve it. It's not really resolved, but you can basically look at the broadening and estimate what the distance is. But the normal, or the workhorse of dipolar spectroscopy is this double electron-electron resonance, and it's also named ELDOR, and I don't know why there are two names, and I think DEAR is the funnier one, so I'll stick with this one. And here, so it's a double electron resonance. So you have two different microwave frequencies. So you have observer channel and the pump channel. And there, if you look at this nitroxide at Q band, you can actually put them at different positions in your spectrum. And then you kind of excite different orientations or different nuclear spin states. But you usually assume that if they are far enough away in the protein and they can wiggle enough that you don't really have correlation between the tensors, and then this works very well. Then let's say you would have two doublets, right, which are split by the dipolar coupling. And if we assume that this coupling is smaller than you get the spacing between these pulses, then what you have is basically a heteronuclear spin echo, right? But we do it for a constant time, because otherwise on top of the oscillations, you also have relaxation. But if you look at the sequence, what you do is that from here to here, you refocus your dipolar coupling. It's basically just because you have a dead time that you do this echo. And then you introduce another selective or a pi pulse only on the pumped spin, sorry, which kind of dephases your spins. But again, from this point here, so in this rectangle, the dipolar coupling refocuses again. But in this time t, so here and here, it actually doesn't refocus. So that's why you see dipolar oscillations. And usually the primary data that you have still looks something like an oscillating decay. But you have to keep in mind that this is not really relaxation, because the total time of the experiment is the same. So what this is intermolecular background, because if you have a spin pair, you also have another electron spin at some distance. And basically, the decay rate of this decay gives you basically something about the concentration. But you can try to do a background correction, which then gives you these nice dipole oscillations. And of course, the frequency of these oscillations is the dipolar coupling. which gives you the distance in the end. And basically how far or how deep this modulation is a measure basically of how many spins you actually invert with a pump spin. So this will usually not be one because you have to use some of the observer basically. But so that's why this is a typical nitroxide DIR. And now I go very quickly through the rest. So we can get distance distribution by regularization because it's an ill-posed problem to get a whole distribution just from this measurement. But there are many papers on this, and this was nicely demonstrated that it's possible. Of course, in biology, it's usually a bit more difficult in real systems, but these distance measurements work very well in the range, which is probably shown here, 2 to 7. If you have a special system and deuterate it, and because Thomas Schmidt is here, we can actually go up to 16 nanometers. Yeah, and I leave this away. So instead of using a pump pulse, you can also do T1 relaxation of the second spin, do the work. And there are also some more complicated sequences where you actually need phase cycling so here this is with double quantum filtering, but I leave this away because I'm already over time. So basically some conclusions would be that, I mean, you see there are a lot of similarities between EPR and NMR, but it's just this difference in magnitudes basically which make all the difference, I would say. And then there are very many technical and instrumental differences. But still many ideas can be adapted. So I think a lot of what our research group is now doing actually with the AWGs, it helps a lot to know the NMR literature. Then DNP is an obvious connection where you kind of need both, and basically paramagnetic NMR would be the same thing from a different side, I would say. Because I just wanted to make some advertisement, shameless, that EPR and NMR are both magnetic resonance techniques, and I think like this this journal by the group Ampere actually shows this very nicely, and of course also the Journal of Magnetic Resonance. There are many things that I didn't cover, which are up and coming. If you want to read more, I think this is a nice and up-to-date book. I think it's from last year. And the good thing is that basically the whole book is also available as individual articles on EMAG-Res. And there's a lot of literature, like also further literature from there. So I think these are very nice chapters if you want to know more. And then I just wanted to quickly acknowledge some people. Basically, these are people that taught me magnetic resonance. And if you start doing such a list, you actually recognize how many people teach you the things. And that's why I also think that these tutorial sessions are a very nice thing. If you want to know more about the research about EPR, you can actually come to our now monthly EPR sessions, which we do since March, and Asif is actually also involved. But this would be it. Yeah. Okay.
So, quick question from an anonymous attendee. Can you comment when spin labels for dipolar spectroscopy and which you would use, RHYTHMI or DIR or DQE?
Okay, that's good that we just do it like this. So, I mean, the standard, I would say, is still nitroxides and DIR. They're just kind of a very good match. But sometimes you might have labels that are just inside your molecule anyway. If you have a paramagnetic ion inside your protein, that might already be chosen for. And there are some other problems for nitroxides, for example, that they are not reduction stable. So if you want to do that, if you want to put them into a cell, they will just be reduced, and you won't have an EPR signal anymore. But then, of course, there are also the spectral properties. So if you look at this copper spectrum, it's very broad. So if you want to use DIR, this pump pulse will hardly do anything, because if you excite one of the spins, most of the pair spins will just be unaffected. So usually you have a very low oscillation on top, and it's a problem in signal to noise. Then you could use AWGs, but only to a certain extent. But for example, this RHYTHMI is very nice for coppers, because instead of pumping, you just store your magnetization along Z, and then you wait until the pair spin relaxed. And this is, of course, this has an infinite bandwidth. Of course, this relaxes, like, it's not necessarily the same for all orientations, but at least usually all of them do it. And there's how this README is, I would say, is very nice for labels with broad spectra. But of course, often the choice is also biochemical and not spectroscopically. So you cannot really distinguish the two. So if you have a specific example or something, maybe I can give more details. But
okay, so talk to Nino for all your EPR questions in specific systems. Okay, why don't you use a mixture of radicals or heteroradicals for DEAR to avoid spin overlap between the pump and the probe?
So we sometimes do, but doesn't, just because you have two radicals doesn't mean that they don't overlap. That's basically the point. If you go at the very start, if you look at tritons and nitroxides, they also overlap. So you still have to use a double resonance technique to do it. Yeah, so it's very rare that you have two different radicals that where the G values are far enough apart and in the right range that they don't overlap at all. Yeah. But there are some cases. But then at some point, again, if you use DEAR, then they are so far apart that you cannot excite them both in the same resonator, which is also not good. So, yeah.
Okay. So I don't see any further questions. Jeffrey is pleased for the plug for magnetic resonance, as he would be. But okay. A quick question from Thomas Schmidt. What do you think about how EPR or NMR can be used conjointly to tackle biological problems? And why don't more people do that?
Well, I mean, I don't know why people don't do it. I think the EPR labs I know that do dipole spectroscopy in biology, many of them actually use NMR as well. So I think it's mostly a question that there are not so many EPR people like doing this at all. So I think there's actually a manpower problem in all of this, but I don't really know. I mean, we do, so I cannot say it from our part. Yeah, but yeah, so I guess education about EPR and having EPR spectrometers probably helps.